Donaldson-Thomas theory. Invariant. This is, roughly speaking, invariant. This is, roughly speaking, counting invariant of modules over a three-dimensional Calabi-Yau algebra. Or more generally, counting invariants of objects in a three-dimensional Calabi-Yau category. So later I will explain what the three-dimensional Calabi-Yau category means, but
why not use the two-dimensional?
Well, this is because, well, let me explain. Well, this is originally introduced by Sendrey, and his original motivation is the following. Let X be a three-dimensional Calabi-Yau. So the answer is because this should be related with three-dimensional Calabi-Yau geometry. Calabi-Yau variety. And assume that we have a certain non-commutative algebra such that the derived category of coherent sheaf on X is equivalent to the derived category of coherent sheaf, derived category of A modules. Under this setting, his proposal is compare the DT theory, Donaldson-Thomas theory for X, and non-commutative Donaldson-Thomas theory for A. So Donaldson-Thomas theory for X is counting invariants. I mean, so first we construct a moduli space of sheaves on X, and then taking Euler characteristics, or more precisely taking virtual counting, we will define such invariants. And his proposal is, under this setting, under this derived equivalence, compare the Donaldson-Thomas theory for X and for A. And actually, in my paper with Nakajima, we compare. We show that these two theories are related by a wall crossing phenomena, and as an application, we provide a explicit description of the generating function of Donaldson-Thomas invariants as an application of wall crossing formula. Of course, in some special setting.
Is Calabi-Yau open?
Pardon?
Is Calabi-Yau open?
Yeah, open. Actually, this is worked for the conifold case, and we have several generalizations, but today I will not talk about this, and what I'm talking is somehow related to the second.
So there must be something slightly more data there than just the equivalence, because somehow the T structure, you're computing stable objects in some T structure, and the T structures don't match. So you need to.
Yeah, we have different T structure.
Crossing going from one.
Yeah, of course. Well, of course, how can I say? Actually, in this paper, we worked on a very special case. And in general, well, how can I say? For example, it is not proved yet that the space of stability condition is connected or not. And, well, philosophically, it is expected that they are connected, and we can connect to T structures by, how can I say, in a path in a space of stability condition. But, yeah.
The wall crossing formulas, would they say that only that the changes in invariance are in some sense finite? That knowing one set of invariants and a bunch of small changes you could get the other ones, or the wall crossing formulas a priori could change everything?
Well, change everything. What do you mean? Well, actually, we have infinitely many walls.
Oh, there are
infinite more walls, yeah. But finally, we can get a closed formula. Yeah. Okay. Yeah, but anyway, today I will not talk about this. And the second motivation is actually using non-commutative or Donaldson-Thomas invariants. We can well, it is expected that we can construct certain geometric structures on the space of stability condition. Stability condition. So there are several works given by Dominic Joyce or Bridgeland Toledano. Or Konchevich and Soiberman. And also Guyot, Moore, and Naitsky. I think tomorrow there will be a talk on this paper. Well, what this means? Well, the space of stability condition is a complex manifold due to Bridgeland, but it is expected that they have much more, how can I say, enriched structure. And, well, we expect that we can construct such structures, enriched structures, using the information of counting invariants of the triangulate category. And, well, so actually what I'm talking today is somehow related to their construction. So let me briefly review Konchevich and Soiberman's construction. So actually what they constructed is torus fibration over the space of stability condition. So let D be a three-dimensional Calabi-Yau triangulate category. So this means we have the following duality. Homomorphism from A to B is canonically dual to the X3 from B to A. So for three-dimensional Calabi-Yau variety, this is a consequence of cell duality. And we assume that this triangulate category has this property. And let T hat be a completion of the group ring of the Grothendieck group of this triangulated category.
You want to assume that this category is smooth and the takes are finite?
Homofinite? Yeah, we assume. Yeah, later I will explain, how can I say, the more concrete setting, but here I will just give you the brief review. So, yeah. So T is, so we can interpret this as a coordinate ring of torus. And so given a triangulated category, we can associate a torus, and we would like to construct a torus vibration over the space of stability condition in the following way. So let A be a core of T structure, and assume that in a space of stability condition, so this is the space of stability condition, and in the space of stability condition, so we assume that we have a stability condition on A. So this gives us open set in a space of stability condition for D. And also assume that we have another core of T structure given by tilting from A. And I will not explain what tilting means, but as a consequence, well, this is not true in general, but as a consequence, space of stability condition for A and for A prime, so both of them determine the open set in a space of stability condition for D, but they have non-trivial intersection. So I mean, I would like to work in such a setting. So roughly speaking, tilting is a shift of the open set in a space of stability condition. And here we have intersection. And in this setting, we can construct a torus automorphism. Torus automorphism. Actually, well, sorry, we can, anyway. Torus automorphism such that, well, what is this? This gives a transition formula for non-commutative Donaldson-Thomas invariant of A and A prime. I mean, if we know the information of non-commutative Donaldson-Thomas invariant for A and the information of this torus automorphism, then we can compute the non-commutative Donaldson-Thomas invariance for A prime. So in this sense, this gives a transition formula, transform, yeah.
So should I think of the non-commutative Donaldson-Thomas invariant as some kind of section of the torus one of this torus?
No, I will explain later, but we can interpret non-commutative Donaldson-Thomas invariant as torus automorphism again. So roughly speaking, dt for A is torus automorphism, and yeah, we can construct Torus automorphism using the information of non-commutative Donaldson-Thomas invariant for A. And this is for A prime. And here we have dt A prime dt, sorry, dt A prime A. Yeah, actually we have plus and minus. Anyway. Well, later I will explain what this means, but roughly speaking, we have such a commutative diagram. And if we know the information of Donaldson-Thomas invariants for A, then we can compute this using this diagram. And this Torus automorphism involves every information of the non-commutative Donaldson-Thomas invariants for A prime. Yeah. So this is the meaning of this automorphism, and actually this is defined using the theory of Motivik Hall algebra and integration map. Introduced by Dominic Joyce. So I mean, the construction of this automorphism is rather abstract. And given such automorphism, we can construct torus fibrillation by patching two trivial torus fibrations on stub A. So this and this, why this torus automorphism. Then we can construct the torus vibration on the whole space. This is a sketch of Konchevich and Soiberman's construction. And so what I'm talking today is, as I said, this torus automorphism is given in an abstract way. So today I will give a description, explicit description of this torus automorphism. And actually this explicit description have several applications in the theory of cluster algebras. But I think most of them are not interested in cluster algebra here. So today I'd like to give you this explicit description. So for any questions? Yeah, so from now on, let me explain the more detail. So I'd like to start with a quiver with a potential. So I don't want to explain what the potential is, but well, quiver is just a directed graph, and well, potential is a kind of additional information. So given a quiver and an additional information, we can construct gamma. This is so-called Ginzburg's DG algebra. And let J be the degree 0 cohomology of gamma. So gamma is DG algebra, and J, well, because we take cohomology with respect to the derivation, this is just an algebra, so-called Jacobi algebra. And let D be the derived category of DG gamma modules. So this is always, pardon? Example of quiver with potential. Well, how can I say? For example, this is a.
Is that same thing what people call pass algebra?
No, different from. This is pass algebra.
Oh, that's pass algebra.
Yeah, but for example, if we take such a quiver, and this is x, y, z, and let x be w be this potential, then so Jacobi algebra is nothing but the coordinate of ring of C3, and in this particular case, this is case isomorphic to Ginzburg algebra. In general, it's not true, but in general, the definition of gamma is a little bit complicated, and I think even the simplest example, this is a little bit complicated. Oh.
It's commutative in this case?
Commutative? In this case, no. DG algebra is, well, actually in this case commutative. Depends on the, in this case, quasi-isomorphic to commutative algebra, but in general, far from commutative. Well, roughly speaking, how can I say? For example, for such a quiver, simple quiver, this is defined by adding such new arrows. Pardon?
What potential do you choose?
There is empty potential. Yeah, in this case, no potential. And I forgot the precise degree. But for each new adding arrows, we put several degrees, which corresponds to the degree of the DG algebra. And also we define the derivation. And in the definition of the derivation, we put the information of the potential. And we construct a DG algebra. And for example, in this case, we put 3 arrows here. And so this is the dual of x and dual of y and dual of z, and 1 loop here. And we construct a certain DG algebra. Yeah, anyway, in this talk, the definition of the Ginzburg algebra is not so important. But the important thing is this is always 3 Calabi-Yau. This is always 3 Calabi-Yau. Sorry, not this. 3 Calabi-Yau. Actually, to be precise, this is not homofinite, so we take a full subcategory consisting of modules with finite dimensional cohomologies. Then the full subcategory is homofinite, and here we have the duality corresponding to the cell duality. But yeah. And also we have natural T structure, and its with hat is isomorphic to the module category of J. J is a path algebra, J is a Jacobi algebra. And in this setting, well, let I be a vertex. Large I is a set of vertices of the quiver Q. And algebra J is decomposed into the projective J modules. So this is projective J modules. And let B be an element of numerical Grothendieck group of D, which is isomorphic to the set of sequence of integers. And given the information of I and such a vector B, we construct the Hilbert scheme, which parameterizes surjections from this projective module to an element in this abelian category A. So this is an analog of the Hilbert scheme on X, which parameterizes surjections from the structure sheaf to a coherent sheaf F. And so projective module is an analog of the structure sheaf. And we work on this abelian category, but as you can see, this is an analog of this Hilbert scheme in the commutative setting. So this is the reason why I wrote here. And Donaldson-Thomas invariant is virtual counting of this moduli space. So we define an analog of Donaldson-Thomas invariant in this setting. Actually, we define the generating function of Donaldson-Thomas invariant as follows. Virtual counting of the Hilbert scheme where this is a monomial.
So why the Hilbert scheme has a symmetry of shocking theory?
Well, roughly speaking, this is because this category is three-dimensional Calabi-Yau. And actually, we can construct this moduli space as a critical locus of potential. And potential function, we can construct a potential function using the information of the potential of the quiver. So this is one of the reasons why we call this as a quiver, a potential of the quiver. Yeah, so actually, the Hilbert scheme is non-compact in general, so we define this as a weighted Euler characteristic weighted by variant function. And variant function is, as I said, the moduli can be described in terms of critical locus, so we can define variant function. So this is the generating function. But this depends on the choice of I. So we encode the information of the generating function for all I into the Torus automorphism in the following way. This maps xi to dt a I y. Where t is a completion, well, of course, completion is always a subtle problem, but and I'd like, well, it's just technical problem in this case, so I'd like to omit the definition of completion. Well, in general, it's very serious problem, but in this particular setting, well, the problem of the completion is not so serious. And why I is given by the following. So here Qji is given, is given by the following. Qji is the number of arrows from j to I minus the number of arrows from I to j. So this is an element in this torus. Sorry, maybe this is plus minus. Roughly speaking, this I y corresponds to the simple module, and xi corresponds to, this is not true in general, but roughly speaking, this is projective module.
So j and I live in the same index?
Yeah, this is, sorry, this is in I, where I is a set of vertices. I is a set of vertices. And n is the size of I. And for each vertex of the quiver, we have corresponding simple modules and projective modules, and roughly speaking, y and x corresponds to their modules, such modules. And starting from a quiver with potential, we get such an automorphism of the torus, which contains the information of the generating function of non-commutative Donaldson-Thomas invariants. So what I'd like to do from now on is to describe the transformation formula of these torus automorphisms.
Are there any cases where the Donaldson-Thomas invariants of computers control RBL category which is not expressible as a quiver with potential?
No, I don't know. Yeah, I think maybe no projective example, and for many open examples we have associated quivers, and I think no. Okay. So as I said, from now on I will describe the transformation formula for this torus automorphism, and let me explain in which setting I will describe the transformation formula. So let Q and omega be the quiver with potential, and take a vertex K. Then we can mutate to get a new quiver with potential. And well, how can I say? Yeah. Then the theorem given by Bernard Keller and Young is the following. We have actually two derived equivalences between the derived category associated to the quiver with potential, the original quiver with potential, and the quiver with potential given by the mutation. And moreover, this derived equivalence is given by tilting. So let me explain the meaning of this theorem. So in a space of stability condition, actually I should divide by the R action given by the rotation. In a space of stability condition, we have an open set corresponding to the original T structure. What I wrote A. And well, and given a vertex K, we have an algorithm to provide a new quiver with potential, and we have a derived equivalence between the of the original quiver with potential and the mutated quiver with potential. And So this is given by tilting. So, but actually this is a kind of the smallest tilting. As I said, tilting is a kind of shift of the open set in a space of stability condition. And here we shift a little bit in a space of stability condition, roughly speaking. And so here we have the module category for the mutated quiver. But actually we have two automorphisms, so two equivalences, and these two. So on this side we have a canonical T structure, and this is a pullback of the canonical T structure on the right hand side with respect to the equivalence. But we have two equivalences, so we have two T structures. So this is a picture of this theorem. And what I'd like to study is a composition of such mutations. I mean, so I'd like to study the transformation formula between two open set, two abelian categories given by composition of such shift. But in general, the composition of tilting is not a tilting anymore. In other words, if we shift this a little bit and a little bit, then finally the original open set and the final open set in general do not have intersection. But we have the following theorem given by Plamondon. Given a sequence of integers, a sequence of vertices, then we have a sequence of signs such that the composition of these derived equivalences so actually these signs epsilon 1, epsilon 2, and epsilon L determines which derived equivalence we will use. I mean, each time we have two choices of derived equivalences. So this is the derived equivalence from the original quiver with potential to the quiver with potential given by successive mutations. And the claim is this is given by tilting. So in the space of stability condition, we have the following picture. So originally we have A, which I denote A0 here. And by a single mutation, we have the following mu ki. So this is the T structure given by single mutation. So for simplicity, let this be A1, and applying the same procedure successively, let this be A2 prime, and so on. And finally, we get AL. This is by definition the pullback of the canonical T structure on this side under this equivalence. So as I said, in general, the composition of tilting is not tilting anymore, but due to this theorem, we have such a situation in a space of stability condition. And the original open set and the final open set has still intersection here. Right. Given any sequence sequence of vertices, we can get a sequence of signs, I mean plus or minus, which determines which automorphism we will choose. So what I'd like to compare is the non-commutative Donaldson-Thomas for this and for this. So actually, in the space of stability condition, this is a special setting, but in order to describe the relation between, actually, this and this does not depend on the choice of signs. Mutation is just determined by the choice of vertices, but we have two equivalences for each vertices. And in order to compare the DT invariance for this and this, I would like to use derived equivalence, but we have, what this theorem says is we have a good choice of derived equivalences. And using, in this setting, we can describe the transformation formula explicitly. So let Qi. This depends on sign, but I mean this. So here I wrote this. This is by definition the composition of mutations. Starting from this quiver with potential, we get applying successive mutations. We get this quiver with potential, and this does not depend on the choice of signs.
So the notation is a bit not incomplete.
Yeah, but the claim is this is determined uniquely. So yeah, maybe I should write. Yeah. So thank you. Yeah. A priori, I should write in this way. Yeah. But I will use. Maybe I will use this. Anyway, so in order to describe the transformation formula, let Qik be the degree 1's cohomology of Pik, where Pik is the projective module over the Jacobi algebra over the mutated quiver. So this is in abelian category A. So this is the module over the Jacobi algebra of the original quiver. So this is so-called a Quiver Grassmannian. This is because Qi is a representation of a quiver, a module over the Jacobi algebra. And, sorry. Yeah, sorry, this is not a Quiver Grassmannian, of course. So let me introduce Quiver Grassmannian of this module. This is just a module. And take B as before. This is an element in the numerical Grothendieck group. And for a vertex I, here we take a vertex I, and for a numerical data B, let grass K I V be the moduli space which parameterizes surjections from Q I K to B, where B is in A and the numerical class of V is given by small v. This is so-called Quiver Grassmannian. And now I will define a torus automorphism using the information of this Quiver Grassmannian. Let dt AL is the final abelian category, and A, this is automorphism of the torus. Actually, in this case, we don't have to take on completion. This is given by the similar equation as before. Grassmannian. So as before, T is a polynomial ring for X, and well, Y is given explicitly. And here is Euler characteristic, topological Euler characteristics of Actually, in this case, we don't have to take virtual counting because the Belen function is 1, so we don't have to take. But the virtual counting coincides with the actual Euler characteristics. But anyway, so using the information of the Quiver Grassmannian, we define such a torus isomorphism. And the first theorem is dt. Well, how can I write? I forgot. dtal is sorry. Here we should define two. Sorry. Minus plus. sorry, here we should introduce two torus isomorphism, which is essentially same. This minus automorphism is given by a kind of twist from the equivalence for plus. But anyway. So the theorem is the transformation formula for dt invariant between, maybe here I should write 0 for, sorry. A0 is the original T structure and AL is the final T structure. And the dt invariant, so this is the torus automorphism containing the information of dt invariant for AL, and this is given by the dt invariant for original Quiver and these two torus isomorphisms given by, this is minus, sorry, given by, so
what is the H1A?
this is, well, A is, this is an element in derived category D, and A gives A is a core of T structure, and this is a cohomology with respect to this T structure. So an element in this derived category gives, well, this is not, well, yeah. This is a cohomology with respect to this T structure. So roughly speaking, an element in the derived category is a complex of abelian category is in A. Of course, this is not true in general, but yeah.
So what is called cluster algebra in this situation?
Cluster algebra? Well, wait a moment. I will explain soon. Yeah. And so this is so-called the transformation formula, because if we know this, the dt for original Quiver and the information of Quiver Grassmannian, we get the information of the mutated Quiver. And if we take L equals to 1, I mean, the sequence of is just a length 1 sequence. So L is the length of this sequence. And in this case, so dt, how can I say? How can I write? Maybe I should write. This is so-called cluster transformation. This is originally observed by Konchevich and Soiberman. They observed that the cluster transformation appear in the transformation formula for non-commutative Donaldson-Thomas invariants under a single mutation. But today I provide a transformation formula for the composition of mutations. And so clearly this satisfies the following condition. So we can compute the transition formula in transformation formula in a two different way. I mean, so this is what I described here. But if we apply for length 0 sequence, actually applying this formula for length 1 sequence, we get cluster transformation formula. And so I wrote such a picture. And if we apply this theorem from here to here directly, this is the left-hand side, and right-hand side is we apply the formula successively. And so this gives is given in terms of Quiver Grassmannian. So this is a kind of application of this theorem. And actually, well, how can I say? Cluster transformation is, well, a kind of, well, actually this is introduced by Formy and Zervinsky in their study of canonical basis of quantum groups. And after that, cluster transformation appears in several very different areas of mathematics. And in each case, this is a kind of, well, this helps, cluster transformation helps us to understand the whole phenomenon in inductive ways. So the study of composition of cluster transformation is in general very important, and this is a kind of categorification of composition of cluster transformations, and actually we get a explicit description in terms of Euler characteristics. And using this description, we have several applications in cluster algebras. But maybe I should stop here. Thank you very much.